A solar cell is essentially a p-n junction with a large surface area. The n-type material is thin to allow light to pass through to the p-n junction. Light travels in packets of energy called photons. The generation of electric current happens inside the depletion zone of the p-n junction. The depletion zone, as explained previously with the diode, is the area around the p-n junction where the electrons from the n-type silicon have diffused into the holes of the p-type material. When a photon of light is absorbed by one of these atoms in the n-type silicon, it will dislodge an electron, creating a free electron and a hole. The free electron and hole have sufficient energy to jump out of the depletion zone. If a wire is connected from the cathode n-type silicon to the anode p-type silicon, electrons will flow through the wire. The electron is attracted to the positive charge of the p-type material and travels through the external load, creating a flow of electric current. The hole created by the dislodged electron is attracted to the negative charge of n-type material and migrates to the back electrical contact. As the electron enters the p-type silicon from the back electrical contact, it combines with the hole, restoring the electrical neutrality.
This is how solar power works. Let's start in the heart of a single solar cell. Particles of light, which we call photons, enter the solar cell and are absorbed by available electrons, exciting the electrons to a higher energy level. Excited electrons travel out of the cell and through an external circuit where they exchange this newly gained energy to do work. The spent electrons return to the cell, ready to absorb more photons. The supply of extra electrons and the force that turns a solar cell into a sort of electron pump or motor comes from joining two special types of silicon material together to generate a reaction where they meet. This is called a p-n junction. Making a p-n junction. A silicon atom has 14 total electrons at various energy levels, or shells, with 4 in its outermost shell. Electrons in the outer shell are used for bonding with other atoms. Stable atoms generally favor 8 electrons in the outer shell, so silicon atoms share electrons when bonding to meet that number. We need extra electrons to do work. It's possible to add small amounts of impurities to silicon that change its molecular structure. This is called doping. N-type silicon, N meaning negative, is doped with phosphorus. Phosphorus has 5 electrons in its outer shell, where 4 are used to bond with neighboring silicon atoms, leaving an extra free electron. P-type silicon, P for positive, is doped with boron, which has 3 electrons in its outer shell, leaving an extra open space or hole when bonding with silicon. When an electron leaves an open spot, other electrons naturally fill it in sequence. For our purposes, it's convenient to track the open space or hole as it moves. In the standard atom model, electrons are represented as having a negative charge. For convenience, in our model, we can think of holes as having a positive charge and track that empty space as it moves through the cell. The space charge region. The space charge region forms at the junction where P and N-type silicon meet. When these doped silicon types are layered, unequal electrons and available spaces, or holes, naturally seek to recombine across the junction, attempting to equalize. However, just because doped silicon creates this intentional electron imbalance doesn't mean the full atoms can simply merge across the gap. Natural forces keep the rest of the atom's structure rigidly in place and intact. Atoms generally have the same number of orbiting electrons as protons in the nucleus, as well as neutrons. And doped silicon does as well. P-type silicon has an extra electron, but also an extra proton. Electrons just naturally move around a lot easier than protons. When these electrons wiggle free and try to equalize, the imbalance creates special, electrically charged atoms with unequal electrons to protons, called ions. Again, even though these atoms are now in the ion state, they're fixed in the silicon structure and won't move. These opposing positively and negatively charged ions eventually prevent further electron and hole diffusion, giving the space charge region a precisely designed width, strength, and so on. An electrical field exists in the space charge region. Excited electrons are attracted and swept in the positive direction, and holes in the negative direction. As such, electrons can't go backwards, and must travel an external circuit to recombine with an open space, instead of simply doing so inside of the cell and wasting their newly gained photon energy as heat. Supporting structures. Let's look at other parts of the solar cell that support the core process. Anti-reflective material. Polished silicon alone wastes a lot of light by reflection, so anti-reflective coating is added, or improved efficiency. There are many types of anti-reflective material. In this example, a grid of microscopic inverted pyramids directs and captures light at many different angles, giving it maximum opportunity to enter the cell and remain longer inside. Photons can be absorbed at any point throughout the cell. For example, short wavelength, high energy blue light is absorbed readily near the surface, while long wavelength, lower energy red light can require more depth or time inside the cell to be absorbed. Front contact. Metallic fingers are screen printed and bonded to the top of the cell. They're designed for optimal charge collection, but minimal shading. Passivation layer. A special coating over the rear surface helps prevent early recombination of electrons and holes, and gives light another chance to bounce through the cell and be absorbed. Aluminum rear contact. A rear aluminum layer completes the electrical circuit. Electrical contacts protrude through the passivation layer. Encapsulant. The encapsulant is an adhesive that seals around the solar cells, protecting them from harmful outside elements and keeping them firmly in place. A common encapsulant material, called EVA, ethyl vinyl acetate, is stable under high temperatures and UV exposure and is also transparent. Glass top layer. A thick layer of low iron glass protects the cell from outside conditions and provides structural strength while also allowing maximum light passage. Low iron reduces the reflective impurities that give normal glass a faint greenish-blue tint. Backsheet. Polyvinyl fluoride film, or Tedlar, forms a thin, near-impenetrable protective back layer to prevent damage to sensitive internal parts during installation and day-to-day function.